And another technique is using the Q learning. Q learning is reinforcement learning technique. Okay. As professor have said already, with the as we evolve more and more, we have intelligent devices and we see a lot of redundant and repeated content request. Okay. So for example, if some movie is released next week on Friday, so what happens? If it comes on Netflix, many of the users will start to download that movies. Okay. So it will create redundant request to the network server. Okay. So to avoid that, we can do edge caching. So this redundant and repeated content request, what does it do? It limits the capacity of front haul and back haul. Okay. So that causes network congestion. Okay, and that causes network failure. Okay, at these routers and other base stations. Okay, because all the file will be delivered again and again, it will cause congestion. So to lower the redundant traffic, edge caching is one of the possible solution, and it's very effective. So when it is the peak time, we can directly deliver the content if we have the content stored. Okay, so for example, at night, nobody, I mean like after like 12 o'clock, nobody watches that much. Okay, so that is like off peak time. But in the morning or the evening time, it's like the peak time. Okay, so in the off peak time, we can download the content in the caches, we can update the content, and the peak time we can deliver the content directly to the user without going to the content server. Okay, that way we can save this bandwidth. Okay, that is the idea for edge caching. Okay. So given the content popularity profile, now what is content popularity? Now to model this problem, what we do, or what engineers do, is researchers do. Internet is like millions of files. Okay, so we only consider a particular set of file. Let's say 10,000. Okay, and these 10,000 file, we find out what is the popularity of these files. Okay, we do not consider like infinite set of files. We only deal with particular set of files. Okay, so and those particular set of files will have some popularity. Okay, so that popularity between 0 and 1 for each file. Okay, so if 10,000 popularity, if we can write that in terms of a vector. Okay, so that vector will be called a content popularity profile for that particular set of library. So library is what? Set of files. Okay. So content placement and delivery have been optimized for various performance measures in literature. So if we have placed some cache here, okay, what we want, we have put our cost here to place the cache. So we want to maximize our cache hit rate. We want to place the content such that it should be used more and more. Okay, so what we want to do, we want to minimize the backhaul latency delay, we want to minimize the server load, we want to minimize the cache miss rate, or we want to maximize the cache hit rate. Okay, these are the popular measures to measure the cache efficiency. Okay. So here this picture show analogy to an inventory problem. So inventory problem you already know. For example, you have a grocery store and you want to store some content, but you do not know what is the popularity in advance. Okay, so for example, let's say some festival is coming, let's say Diwali is coming. Okay, if you are a popular businessman, you already know what is going to be popular in next day, then you will store that content. But if you are new to the business, you do not know that much. Okay, so you need to know what is the popularity in advance, but it is also possible the next day the sale isn't that much. Okay, so what I mean to say here is that the content popularity it is not known in advance. Okay, so the next day what content is going to be popular, you do not know in advance. What content is being requested by the user after you have cached is not known in advance. Okay, we will know after the next day. Okay, So that leads to the dynamic caching. So this content popularity profile is not known in advance and need to be estimated from past observation. So if you are a popular businessman, you will estimate what is going to be popular this much, and you know the surrounding area, how much shops are there, and how it's going to be popular. Okay? So based on the past observation, you can estimate. And there are other approaches also, like deep learning based prediction that requires huge training data. And we have autoregressive based prediction also. We have linear prediction also. And there are other approaches like to learn the content popularity independently across content. Online policy for cache awareness, these are some references. And low complexity video caching, this is also one of the approach for only for video caching. And another approach is for user preference learning. We deal with each individual user and try to learn each user preference, and then we place the content in our cache. Okay? So did you understand the problem? Problem is we do not know the content popularity profile in advance, and we want to store the content. What content should we cache? Okay? So for the dynamic caching, if we are doing with learning, we need to assume some assumption. Okay? So assume the content popularity profile varying as a finite state Markov chain. Why Markov chain? Markov chain means it depends on the previous. So it means to say the popularity will not decrease abruptly. Okay? If some content is popular today, it will be less popular today or least popular today, and it will slowly degrade, or it will slowly increase. It will not degrade abruptly. For example, if a movie is released today, its popularity will decrease little by little in the upcoming days. It will not go abruptly. Okay? So for assuming Markov chain, Q-learning approach have been presented, and there are also function approximation Q-learning approach are also there, and multi-agent approach are also there, and some deep learning based RL approach are also there. So they are different reinforcement based learning approaches. Okay? So now we present the system model for the geographical caching that we are going to use for the caching for these online popularity prediction and learning. Okay? So this is a very simple example here. So we have assumed the base station and the users are distributed as Poisson point process, PPP. Okay? Poisson point process means you take the for example, base station is distributed as Poisson point process. What does it mean? You take the number of base station as Poisson random variable. Okay? You generate that number, and you place the base station uniformly in this area, that much number. Okay? So let's say I generated a Poisson random variable with some mean, let's say 10 or 7. So I placed 7 base station here, uniformly distributed in that area. That is also random. Okay? Similarly, I can put the users. Okay? So lambda BS denotes the density of the base station. Similarly, I can denote the density of the base station for the users. And I assume base station and users have single antenna, and cache is available at the base station. So this example shows each base station has three sizes of cache. Okay? And content library is F, and these are the indices for those content. And assuming large number of requests, I can assume my true content popularity, PT is given by, so this is the content popularity profile in a vector form. So PT1 up to PTN for time t, and it should be sum to 1. So I have normalized it. So it will represent like a probability vector. Okay? So in this example, let's consider, let's say these colored users indicate that this user wants green file, and this user want a pink file, this user want green file, this one want gray file. Okay? And for example, this base station, it has this teal file, and this is gray file, and this is orange file. Okay? So if this user want green file, it will request to the base station which has the file. Okay? So nearby base station, this has the file. Although this base station is nearer, but this base station has the file, so it will deliver the file, not this. Okay? So this way, we can associate the users with the base station. So this is the random content placement policy. So earlier we have the, what is the probability? This is the content probability. Okay. Now we have another type of probabilities. These are called the network caching probabilities. So these probability denote how much the base station holds the content. Okay. So let's say this probability QT1, this is for a whole network. Okay. So let's say this probability is, let's say 0.7. Okay. So it means, let's say we have 100 base station, it means 70% of the base station will have this first file. So we have n files here. So this probability is for each file. Okay. So this is the network caching probability. Okay. So these probabilities, one is P and one is Q. So P is from user side. This much content is popular. And Q is from base station side. It means what is the probability that the content is present at the base station. Okay. So this process represent, if you know these probabilities, how will you place the content, how will you generate a realization at the base station. Okay. So let's say if Q is given by, Q vector is given by these 0.9, 0.7, 0.6, 0.55, 0.45, 0.4, 0.3, 0.1. So I can represent like this, and this total will be sum up to L, and L is equal to 4, and we have how many files? 8 files. Okay. So I can, this total is up to 4, so I can divide this into 4, and I can arrange them in terms of this stacks like this. So first is like this, and second is like this, and third is like this. Okay. So I can take a random number and take a snapshot here. So what will I get? Blue, cyan, yellow, and red. Okay. So that way, if I want to place the content, I know these probabilities, but I want to place the content in the cache. So what content I should place in the cache according to these probabilities. So this is how I will do. Okay. I will make this kind of color diagram, and I will take a uniformly random number between 0 and 1, and I will take a snapshot here, and I will get this red, yellow, cyan, and blue. I will put those files in 4 base station. Okay. Similarly, I can take another snapshot. Let's say if some line comes here, I will store this pink, yellow, green, and blue file. Okay. So if Q is larger, it means, let's say this blue is larger, so it means this file will be presented almost all of the base stations. Okay. So this is the way of placing the content in the cache of the base station. So this is the analysis for the SINR. So here, this user wants green file, and it will get the green file from this. Okay. And what other base station have green file? This one, and this one. So they will interfere with this. Okay. And rest of which will also interfere if they are transmitting, but their interference will be different. Okay. So from the Sylvaniak-Mackay theorem, we can analyze the performance from a typical user point of view. And that typical user, we can write the SINR for a given file and for a typical user by this mod of HK square P RK to the power minus alpha. Alpha is path loss exponent, RK is the distance from here to here, and IFK and IFC. So IFK represent the interference from these red lines, those who have files, FF files. IFC means those who do not have the files, and sigma square is the noise. Okay. So this is the interference limited system where interference is much larger than the noise. So we have 2 goals here. So one is to maximize the average success probability. We can successfully deliver the content. And second goal is the prediction. So we can accurately predict what is popularity going to be. Okay. So what is success probability? Success probability is defined as the probability that achievable rate of a system, rate of a typical user exceed the rate requirement. So we considered a typical user, that green user, and that green user have this much rate. If it exceeds some rate, that probability, the average of that probability will be given by the success probability. So that is for a particular file, GQF. Okay, so it depends on the caching probability. If we can average for all the files, it will be denoted as the average success probability. Okay. So this is for the success probability. Now for the prediction, we can define these measures that we want to minimize. Okay. So first measure is the prediction measure. So we want to minimize this error. Okay. Second is the observed and the expected ASP difference. ASP is average success probability. So this P is this is the same thing. Okay. So we are given this P value and Q value. These are the true value. Okay. These are not known in advance, but we want to compare how much we are getting close to it. So that's why we are taking this. We want to minimize this value. Okay. This measure. Okay. So the observed ASP difference is this value minus this, because we have observed P T hat, the estimated one. Okay. And here what we have done, this is the expected. So we have also put P hat star T, P hat T also here. Okay. So this is the expected. So these two are almost similar. If we can bound some one of them, it will other will also be bounded. So this is the lemma. So here in the lemma, what we did, we solved this expression. This is a very lengthy proof. You can see the paper. Okay. So we solve this and we get this expression. Okay, where A, B, C are the coefficient, depends on the physical layer parameters like number of antenna, transmit power, bandwidth, okay, and number of user, density of base station, okay, rate and bandwidth here. Okay. So this looks nice because these are very simple constant and we can now optimize this. Okay. So let me read. For a PPP network with interference limited scenario where the noise is negligible compared to the interference, the success probability for a typical user can be obtained as this. Okay. Now let's come to the techniques. So there are two techniques. One is prediction and second is learning. So first is the ASP maximization. Okay. So the ASP expression that we have formulated, derived in terms of A, B, and C, we can write the average success probability that is PS, that is in terms of PQ. Given the P, we want to maximize Q, and Q is the constraint with respect to cache. Okay. So if we maximize it, we get this expression. So this problem is non-negative least square problem. You can see the paper if you like. This is also a long derivation, and this algorithm also given there. So what we see here, so there are three quantities here. What does it denote? If content is very popular, probability is very, very high in P, we will certainly store the content. If probability is very, very low, we will not store the content. Okay. If content probability is like in middle, like 0.5 or something, we need to check. Okay. We need to do it intelligently. Okay. So we need to think about the probability that are in the middle. If content is very, very popular, we almost surely need to store it. Okay. Here you see one more observation is that this QF depends on this P bar. P bar is what? Square root of P. Okay. And these set R, P, and Z, it will depend on the threshold. When you solve this optimization problem, the threshold will come and it will be based on A, B, and C parameters. Okay. And the popularity measure, this probability, this profile P. Okay. So let's come to the prediction method. So in the prediction method, the first is the popularity prediction method. So here we consider a simple prediction method. So this is the linear prediction. Okay. So this equation says that at the time t, it can be considered as a linear combination of the previous d popularity profile. Okay. So here one thing you note, we consider C in R. Okay. It means if we consider C to be, let's say if we consider C to be positive, it means this P1 and P2. The P3 will come in the between. Okay. If P3 is outside, we cannot predict it if C is greater than 0. Okay. If C is in R, we can also predict P3. Okay. And this is the probability vector, so it should be sum to 1. So based on this, based on this dth order linear prediction model, given the tau observation, we can write the least square problem here. Okay. So this is the least square problem where the all coefficients sum to 1 and the predicted popularity at time t plus 1 is non-negative. It should be non-negative and it should be sum to 1. So it should be sum to 1. This constraint come here. Okay. So we solve this, we will get Ck and Pt plus 1. Okay. So this will be the prediction. So for this ppm, we analyze this delta t plus 1. So we get this expression. So what does it say? So there is this term coming and this p bar is coming. So it shows that ASP is close to maximum as Cp of the mid popular content are close to uniform. Okay. So this comes, it shows that it should be uniform distribution, because if it is uniform, so all probability will be equal, right? So it means if it is actually equal to uniform distribution, it will be 0. Okay. Only for the mid popular content. Okay. So there were 3 sets here, R, P and Z. So the third set, the middle set is P. Okay. Second prediction model is Grassmannian prediction model. Any question up to this point for this popularity prediction? ABC are the physical layer parameters. So it depends on the this density of base station, bandwidth, number of antenna, and the rate requirement. We have covered this here. No, here. This A, B, and C. These are here.
Yeah, please explain that term, sir. I mean,
These term.
What is lambda base station?
Lambda is the density of base station. R0 is the rate requirement. W is the bandwidth, and this S0 is this thing. Alpha is the path loss exponent. This is the integration. Same thing here.
Another thing, sir.
Yeah.
Base stations are, you're considering the small base stations as macro base stations.
Small base stations.
Small base stations.
Small base stations. Yeah. So this is one of the prediction method. Second is the Grassmannian prediction model. So why this is important? Because if we have maximized this, okay, we note that this QF, the content placement depends on this P bar here and P bar here. So P bar is what? Is square root of P. Okay. So square root of P, it depends. Okay. So if we have some popularity vector P that is sum to 1, and if we take the square root, so it means this norm should be 1. So this vector P bar lies on the Grassmannian manifold. Okay. So this leads to Grassmannian prediction model. So from the optimization problem, it can be observed the positive square root of the CP maximizes ASP. So SCP means square root of content popularity vector. So this represents a line in the Grassmannian manifold. So similar to PPP, we can model the problem in linear prediction. However, this is P bar instead of P here. Okay. And similarly, we can formulate the least square problem, but here we have norm here, and these are sum to 1, and it should be non-negative. Okay, so we can solve this using CVX. Okay, everybody know about the CVX, right? So let's come to the learning method. So the results of them I will show here in this next section. Okay. So online learning technique is like learning means we have to learn something that is fixed. For example, if you are in a building, if you are new to a building, you explore it again and again. You want to find something. You want to learn the pattern of the building. Okay. So it means you want to learn. You will ask some question. You will explore. You will make mistakes. Okay. So that is learning. Okay. So online learning is the process of answering a sequence of questions given maybe partial knowledge of the given knowledge of correct answer to previous question and possibly additional available information. So it means when you for example, you go to a building and you don't know what is the pattern and you want to reach let's say Kalpana madam office, you will not able to find it. So you will go again and again, you will ask somebody, you may also go to the wrong door. Okay. So it means you are try to find the answer of some question, whether I should go left, I should go right, I should go straight. Okay. So learning is performed in a sequence of consecutive rounds where at round T, the learner is given a question, that is let's say xt, and is required to provide an answer to this question, say the prediction pt. Okay. So after the prediction, the correct answer is revealed. Okay. So when you have found the Kalpana madam office, your answer is revealed. You should have gone to left, you should have gone to right, then left, you would have reached there. The learner suffers a loss L, PT, YT. So Y is, for example, Y is a set of 0, 1 for online classification problem. So either let's say some classification problem you might have heard of, let's say 2 classes classification problem. So you can select Y equals to 0 and 1. So learner's ultimate goal is to minimize the cumulative loss suffered along its run, which translates to making few prediction mistakes. So it means you have to find the your answer as soon as possible. Okay. So for example, you want to learn the architecture of the building, how it is. You want to reach the Kalpana madam office. So you want to minimize your mistakes. You have to find as soon as possible without making much mistakes, even if you are new. Okay, that is learning. The first approach in this learning is the weighted follow the leader. Okay, so here this is the problem for the weighted follow the leader. So what does it mean? So Wi represents the weight, and I am given this observation up to time t, and I want to predict pt plus 1. So P represent what? Popularity. So I have been given the information up to like time t, and I want to predict t plus 1. Okay. So this is my optimization problem. This problem is sum of norms. Norm is convex. So sum of norm is also convex. So this problem is convex. I can solve it. You can also solve using the pen and paper, using this by taking the differentiation, and you can solve this, you can come up with this solution. Okay. So this solution I can also write in terms of previous observation. Okay. So what this equation denotes here, so this is the true observation and this is the predicted observation. Okay. So the new observation, new prediction is equal to the weighted combination of the predicted observation and the true information. Okay. So W represents the weight, how much you want to weight that observation. Okay. You want to weight your prediction more, so you can choose W accordingly. And if you want to weight your actual prediction more, you can weight accordingly. Okay. So one way to choose weights is by this exponential function. Okay. So I choose weights like Wi equals to kappa t a to the power t minus I. So we have the constraint weight should be sum to 1. So if weight should be sum to 1, I can compute this value of kappa t equals to 1 minus a divided by 1 minus a to the power t. And if I choose a equals to 1, it means wi equals to 1 by t. It means I am just taking the mean of the previous observation. Okay, if a is less than 1, it means it weights recent observation more. Okay. Is this okay? So regret. So in the learning, we calculate the regret. So the regret is defined by this. So at the end of round t, so learning happens in rounds, right? So at the end of round t, what is your regret? So if you are given some prediction p, so you can define your regret like this. If what is your actual minus what is your predicted, so that is your regret. I mean, for example, if you want to go to Kalpana ma'am office, you would have minimized like this much of time, or and actually what could have been. So if you take the difference of those, that is the regret. Okay, and by this process you can bound the regret. So I get this OT. OT means it depends on the t. T is the number of round. It means as the number of t increases, my regret increases. Okay. So if we are getting less than OT, it is good. It means we are learning good. If we are getting more than t, it means we are not learning. Our error is increasing. Our regret is increasing. Okay. So if we are getting less than OT, we are good. So for a equals to 1, we see that we are getting O log t regret. Okay. So up to OT or less than OT, if your algorithm is getting the regret OT or less than OT, it is good. Okay. So okay, these are a simple calculation. If you see the paper, you can find out details of each of the expression. Okay. So this is I have written in terms of algorithmic format. So for each round, what will I do? I will choose the weight like this. Then I will do this prediction based on the previous true observation and the predicted observation. Then after I have predicted, I will observe this. Okay. So this is like a grocery example you can think of. Like I have placed after the next day, you will find what is the true content popularity after the end of day, right? So this is like after that you will find what is the popularity after your prediction. Okay. So similarly, I can also calculate the ASP regret, which comes out to be OT. ASP regret is defined by like this. Okay. So next algorithm, any question up to this point? Am I going fast? Okay. So the next question is next topic is the weighted follow the regularized leader. So here, so this we maximize the ASP. ASP is average success probability. We presented one theorem. In that theorem, the content placement probability depends on the square root of content popularity. The similar observation leads to this approach, weighted follow the regularized leader. So if you have two vectors in Grassmannian manifold, you can measure the distance between them using the caudal distance. Okay. So caudal distance is given by like this, dc square p1 p2 if you have two vectors, which is given by 1 minus, this is like the correlation. Okay. So minimizing the caudal distance is equivalent to maximizing the correlation, that is a cross product. Okay. So the learning problem, what we have maximized here, the weighted combination of these cross products. Okay. So this problem you can solve and its answer come out to be like this. Okay. Here you note that instead of this sum constraint, I have this norm constraint. Okay. Because this is square root. Okay. And weights you can select similar to the previous weighted follow the leader, WFTL. Okay. Any question here?
Sir, you told that you mentioned that you are
deep learning algorithm,
somewhere
I'm using reinforcement learning algorithm. So deep learning I'm not using here in this paper. So I have these three methods here. One is prediction method, second is online learning, and third is reinforcement learning. And reinforcement learning, I have also two other methods, function approximation and conventional learning. Okay. So for this formulation, we can also reduce it to this expression. So this expression shows what? It is like the weighted combination of the previous square root of content popularity and the predicted square root of content popularity. Okay? So this equation obtained from the diagonal inequality. So similar to the previous W weighted follow the leader, we can calculate the regret here, and it also comes out to be OT, and for A equals to 1, we get O log T regret. Okay? So this is the W4L algorithm, weighted follow the regularized leader. So we initialize with kappa equals to 0 for each round. We initialize with W, and we calculate, we predict this, and then we normalize by this kappa T and observe the next observation, and so on. Hmm?
initial weights, but WT equal to 1 minus A,
1 minus A divided by 1 minus A to the power T. A we can choose 1 or less than 1. Between 0 to 1 we can choose. No, fraction values. This A is here. Yeah. A is less than 1. We have weights like this. Yeah. I have chosen maximum value A is for 1. It means if we choose equals to 1, it means we are choosing just the mean of it. If we choose less than A, it means we are weighing recent observation more. If we choose like greater than A, it means we are choosing past observation more. I mean, we are weighting the past observation more. Okay? I mean, that is like not recommended. Okay, so let's come to the simulation result. So we have considered movie lens dataset. Movie lens dataset is a set of movies, okay, where ratings are provided, dates are provided, and the timestamps are provided by different users, multiple of users. So we consider 1024 movies for our simulation, and we consider the content popularity profile obtained by the normalizing the rating across those movies. Okay. So if movie is rated that much, it means it is that much popular. So for prediction model, we choose fourth order model with 10 observation, and for online learning, we choose A equals to 1, and for these are the PPP parameters, Poisson point process parameter, lambda BS, W, alpha, R naught, and L. L is the cache size, 32. And for comparison, we choose two other methods. One is request prediction model. So we generate the random number of requests from user and try to generate using the use the auto-regressive model to predict the number of requests. That is an integer. So we predict the request in terms of integer, then we normalize it and compare it. And second is the mean guessing. Mean guessing is when we just take the mean of the previous request. Okay. This is the overview. Okay, so let's first see the result, then we go to the overview. So these are the all of the methods here. So autoregressive method is the number of requests we will predict by the autoregressive process. These are the FTL and 4L method. Mean guessing means we are just taking the mean of the dth order. Okay, and these are the PPM, GPM. Those are also dth order. So this method is good for the MSE minimization, and square root of content popularity is related to the ASP. So this is good for ASP minimization, and this is 4L will also include the square root of P. So this is also for the ASP regret minimization good. And this is related to the MSE regret, okay? And this is suboptimal because it also relates to ppm. Let's say if we take ck equals to 1 by d, it reduces to this, okay? And it also relates to this one. Let's say if we, instead of t, we take limited number of observation, it's also related to this. So this has the in-between performance of this. So this is the MSE and DASP. DASP means difference of ASP. So optimum value minus the actual achieved ASP value, okay? So here we see that, so for MSE, these two methods, orange and yellow, that is the GPM and PPM, that is the prediction method. OP methods, online prediction methods, works well. And for the DASP method, we have this orange, that is GPM. GPM is Grassmannian. So Grassmannian performing good here because Grassmannian relates to the ASP minimization, okay? So it minimizes the ASP, okay? And the other are, so mean guessing is equivalent to trivial OP. I mean, if we reduce CK equals to 1 by D, that is trivial OP, online prediction, and suboptimal OL FTL. If we reduce the number of observation, it's related to that, okay? So these are the regret. So here are the rounds here. On the x-axis is the round, and the y-axis, there is the MSE regret. There is the ASP regret here. So we want to minimize the regret. So you see here, we have this red line here. So for regret, we computed for what? Online learning algorithm, okay? So learning should perform better here, okay? So here we perform only single metric for overall, and here we perform regret. Okay, so prediction method should work better here, and learning method should work better here for regret. Okay. So here you see this red is OLFTL. OLFTL is working good for MSE regret, and here you see this green. Green is for 4L. 4L is related to the square root of content popularity. So square root of content popularity is related to the ASP minimization. So ASP regret is minimized by this green curve, okay? And OLFTL is also in close with this green curve, okay? So why we have plotted this? This also show the trend. For trend means we said that this is OT and O log T. That thing we can also see. This is the log scale, and this is the T. If it is going very high, it means it is going larger than OT. Okay, so whatever we have seen in theory, we can also verify here. Okay, that's the purpose here. So this is DASP, difference of ASP versus cache size. So if we increase the cache size, what will happen? We can store more and more content. We can deliver more and more content. My ASP will be high. Okay, so difference in ASP will reduce. Okay. So difference in ASP is getting reduced. And here, so I'm choosing ASP difference. So this blue is for online so this is not regret. So online prediction method will work here, good here. So these blue methods are performing better here. Okay. Online prediction. This is with respect to the content library size. If I increase the library size, what will happen? Okay, so our MSC is showing to decrease here, and ASP difference is also being decreased here. Okay, and here I have chosen the cache to be half of the content library. Okay, so these are results for the content, online prediction and online learning, two methods. If we have time, we can go for the Q learning also. We have time? Reinforcement learning.
What is the time complexity for these all?
time complexity is these are online, so time complexity is very, very low. So you see here, so this is just one square root, one division here, and two multiplication, one addition here, and here one division here. To time complexity is not much. Okay. So that's why they are called online algorithm. Online means they can be deployed in real time with very less complexity.
Is it, did you use this process to the online downloading?
Online downloading.
Yes, you said you use the downloading faster than the old one.
So these are for prediction and learning. So we are doing this P here. So P means prediction. So downloading is a different part. So first we have to store in the cache at the base station. So that base station will store cache. When it will cache? At the off-peak period, when users are not downloading. So that part, so it need to estimate what it should do, what it should cache. Okay. So for example, you have grocery store, you will store the content when? At night or when in the morning, when users are not there, and you will store the content based on user request, whatever the content was popular the previous day. Okay, or you will estimate that. So what we are doing here, we are trying to learn based on the previous request, we are trying to learn what is the popularity of the content. Then we will place the content accordingly. Okay. And after the next day, we will observe what is the true popularity. Okay.
If you have energy, please tell about the learning method.
Yeah, okay.
If you have energy only.
Yeah, it's fine. So in the Q learning, we adopt a similar model. So here we have chosen massive MIMO also, massive MIMO base station with single antenna users, and both are distributed as homogeneous Poisson point process. And each user is connected to its nearest base station, which has the file, desired file. Okay. So here we have considered only two color file here. Red means the file F, and the base station blue means other files. And this is the Voronoi region. You can plot in MATLAB, okay, if you want. So Voronoi region based on base station having FF content in their caches. Okay, so based on red, this Voronoi region is plotted here. So similar to the previous, we can use the Selvignac-Mackey theorem to analyze for stationary and homogeneity of the PPP. A typical user at origin can be considered for performance evaluation, and the typical user we can write the SINR equation where this is what? This is the desired signal power. This is what? This is the interference, inter-user interference, I mean like intra-cell interference. So one base station is transmitting to multiple users, so it will be intra-cell interference because it will contain the signal of all other users, and this is the interference from other base station. So this is interference from base station, those who have the same file and those who do not have the same file, and this is the noise variance. Okay. And W is the precoding we have used. So similar, professor have mentioned, we are using MRT precoding for massive MIMO base station. Okay. We can also use geoforcing also. So HK is the concatenated channel for the kth base station. Okay. And this is what? This is geoforcing precoding. You have seen that, right? So this is geoforcing precoding. If we consider geoforcing precoding, inter-cell interference get eliminated. Okay. So we will get this term. Okay. So here, this first term will get 0 if we assume geoforcing, and these three terms will remain. So I have combined these two terms here, and this is the noise term. Okay. And PT is the transmit power. If I assume MRT, my expression of W will be like this, and my SINR will be like this, and this term will be there, intra-cell interference. Okay. So this factor of M is the number of antenna. This is called the massive MIMO gain or array gain. Okay. So this factor increases the SINR. So this is important. Okay. You can see the details of each and every step in the paper also. Okay. As much you want, I can finish it early.
Yeah, I want the participants to learn at the same time. I told the other faculty members that,
Okay.
yeah, they can interact with the professor and the project.
Okay, okay, okay. So what do you want? We can do it later, so if you want.
Yeah, please, I mean, okay, sir, you also please learn.
We can do it tomorrow if you want.
Yeah, maybe you can sit with the professor and interact, sir, while it goes on with the.
No, I thought we can move to some other room.
Yes, please take the professor to your room, sir. Sai Prakash garu. Sai Prakash garu, please take. Please go to Sai Prakash, sir.
So here also we compute the, analyze the average success probability. So this is the success probability. Like previously, we have assumed single antenna in the online learning work. Here have assumed massive MIMO, and the expression is same here, but the derivation is different because of massive MIMO. Okay, so we will get some expression of something of this kind. Okay, where these are different details. Okay, so you do not worry about these details. You only worry about this the factor Q here, and how it is how the noise and the transmit power are doing this affecting this expression. Okay, so for interference limited case, we can get nice expression here, QF divided by 2B QF 2A minus 2B plus 1. So here the success probability is independent of the density of the base station and user. So that is an important observation. So why does it do? So it depends only on the caching probabilities here, and the reason is that the strength of the both desired signal and interference increase with the increase in the density of base station. So if we increase in the density of base station, it means base station comes closer and closer. Okay, so base station comes closer, both the desired signal intensity and the interference signal intensity will also increase. So you have the SINR expression, right? So it means numerator will also increase, denominator will also increase. So ratio will not change that much. Okay, so that's why this expression comes out to be independent of the density of base station and the users. Okay. So this is the, so earlier we were getting some exponential here. Okay, if we do exponential approximation, we can also simplify that expression like this. Okay, so we will use this expression for Q learning also, and we will use this expression also for Q learning. So we will use this expression to propose a new method for Q learning. Okay. So with this expression, we can find out the average success probability across all the files. So this is across one file, GQF, for the fth file. We can average, we can get for all the files. Okay. So Q learning. So this is the terminology for the Q learning. So let me go quickly. So environment. So environment is a time varying system which upon taking action, it gives some observation and also gives some reward. Okay. Agent is the actor who takes the action in that environment. State is a tuple of values which defines the instant of an environment. Action, it is a required input signal to reach the goal. If you have to go something, if you want to learn something, you have to take a step, you have to take the action. Okay. So without action, there is no learning. Reward is a measure of states and action towards the goal. Discount factor weights the recent and future rewards. Okay, how much you want to weigh your previous action, previous rewards, you can choose the discount factor. Okay, so for example, your currency value today is not be the same tomorrow or after year. Okay, so that is the discount factor. So let's say 1 rupee value, let's say 10 years ago, it has much of a value, but 1 rupee today doesn't have any value that much. Okay. Transition probability means going from state 1 to state 2 when taking action A1. That is the transition probability. And there is another term called the state value function, which is defined as the set of actions starting from the present state S0, and this is defined as the cumulative sum of discounted rewards given the starting state S0. Okay? And we can use the Bellman equation to find the Q function. Q function is what? The state action value function. Okay? And people also call it critic function. Okay? So Q function, for the optimal value of Q, we can find out like this. Okay? So this is based on expectation. So its true value we do not know. Okay? We can only estimate its true value, its optimal value. So if we have optimal value, this Bellman equation will be true for that. Okay? So we can also define the temporal difference. This is the instantaneous reward, and this is the Q value. Okay? If we take the difference, we will get the temporal difference. Okay? So this is just a toy example for Q learning. You can also find this in MATLAB also. Okay? You can also try to write your own program in MATLAB using this. If we have time, I can explain, or I can skip it, or go to my results.
Sir, I am again and I am asking if you have energy.
Yeah.
If you have energy, explain, otherwise please translate, sir.
Okay, okay.
Yeah, sorry, he's fasting today, that's why I'm asking again and again.
It's fine, it's fine, it's fine. It's fine. It's fine. So you have time, right? I am asking only for time. Okay. So here, this is the system here. So you have 5 cross 5 grid. Okay. So you are starting from some random state and you want to reach at the terminal state. Okay. When you reach the terminal state, you will get the reward plus 10, and these are the blocks that you cannot cross. Okay. These are the blockage that you cannot go. Okay. And this is your, let's say, agent. Okay. So agent begin from cell, let's say 2, 1, and agent receive a reward of plus 10 if it reaches the 5 cross 5, that is blue. And agent is blocked by obstacle, that is black cells, and environment contains a special jump. So this is the special jump. Okay. So I have also programmed for this. If you want, I can also show you. Okay. So I can go from here to here if I will get plus 5 reward. Okay. And all other action result in minus 1 reward. If I go from here to here, here to here, I will get minus 1 reward. So Q matrix, we have to learn a Q matrix that will be 25 cross 4. 25 is what? Number of states. 4 is what? Number of actions. I can go north, east, west, south, up, down, left, right. Okay, 4 actions and 25 states. We can have 25 states. And these we cannot go. Okay. So Q learning is a trial and error based learning process. Okay. We also take random action, we also take greedy action, and we learn. So where sequential decisions are taken to reach the goal. So model free means it doesn't require the model of the environment and can handle problem with stochastic transition. It means random transition and rewards without requiring adaptations. So minimizing the squared TD, TD means temporal difference, that we have shown here. Okay, this slide. If we minimize the squared TD by gradient descent, it will give us the Q update equation. So finally, what we have to do in Q learning, we have to find these Q values. Okay, Q values for each state. So here in this, my Q matrix is 25 cross 4. So if I find this Q matrix for 25 cross 4, I will find in each state what action I have to take. Okay. So let's say I am here, Q2, 1. So this will be, let's say 1, 2, 3, 4, 5, 6 entry. So in this matrix, 6th entry, I will have 4 values. I can choose that value accordingly. Whatever the value is maximum, I will choose that value to go to that action. Okay. I have to go left, right, up and down, so that I will reach my terminal point as soon as possible. That is learning. So this is the update equation. So what I am writing here, Q, this is the state, okay, and this is the action, this is for time t, and this is for time t minus 1. So this is the update equation, okay. So plus beta t. So this is the gradient descent. So this value is given by like this. This is the temporal difference, okay. So this is what reward plus discount factor max with respect to a qt minus 1, this value, the previous state, okay. Now this is the next state, okay, and qt minus 1, 2 comma 1, 2, okay. So 2 comma 1 I am taking action 2, okay. So 2 comma 1 I am taking action 2, 2 means south, so I will went to 3 comma 1 state, okay. So this is the next state, okay. So this is the process of Q learning. So what happens here, first we initialize the Q values. So 25 cross 4 matrix I will initialize to 0, okay. Then for each episode, so I have given an example for, let's say, building. You want to learn the pattern of a building. You go one time, for example, you want to find the Kalpana Madam office. So that is like the terminal state, okay. Your starting point is the gate, okay. You went and you go around, you go to the 3rd floor, 4th floor, 5th floor, 6th floor, and you somehow went to Kalpana Madam office. So that is your one round complete, okay. So that is one round, and when you do this round multiple times, you will learn, okay. So that round is also called the episode, okay. In one episode, how much you are learning. So I have run for some episodes here, and for t equals to steps. So when in each round you will take some steps, you will knock at the door, is this Kalpana Madam office, or you will see something, okay. So that is the taking steps. You have to go left, you have to go right, okay. So that is like taking steps. So in each episode, in each round, you will take the steps, okay. And now those steps, let's come to those steps. How will you choose the step? There can be two possibilities. Either you choose greedily or either you choose random, okay. So this is the random step. So U means uniform distribution between these all possible action. I can choose uniformly with probability epsilon. So that's why this type of action is called the epsilon greedy action. Okay. So it means you want to go randomly. A second thing, you want to go greedy. Greedy means whatever the information you have, you will go according to that information to maximize the Q value here, okay. So you will choose that action. So here one is exploration and one is exploitation, okay. So there is a trade-off between exploration and exploitation, okay. So this factor epsilon controls that trade-off. If I make this epsilon larger, it means I am taking more random action, okay. If I make it smaller, it means I am taking more greedy action, okay. So when we are learning, we have to control that epsilon accordingly. So in larger episode, we can reduce the epsilon. In the earlier episode, we can make the epsilon larger, okay, to learn more efficiently, okay. So after we have taken action, I will go to next state. So for example, here I have taken some south action. I will go to 3 comma 1, and then I will get some reward -1 here, and then after getting reward, I will update my Q value using the equation that I have shown earlier, okay. So this is the process, and after that I can update my epsilon also, I can update my beta also, okay. So this is the process for Q learning development. So this is conventional Q learning, okay. For this also I have code also, simulation also, I can show you, okay. Now for edge caching. So edge caching also happens in time slots, okay. So there are 3 time slots here. One is content delivery. Any problem? Okay.
Continue. How many of you want to go for lunch immediately?
Not for immediate, but it's a next topic. So I will go to the next topic. So
15 minutes.
What do you say? Okay, I mean, let us stop here because, yeah, even though he's not telling, I feel, what to say, pity for him.
Okay, we will in the next class, maybe I can show you the code also tomorrow maybe,
Yeah,
and complete this also,
Yeah,
okay?
tomorrow you please handle.
Yeah, yeah, yeah.
So, we will expect a simulation from the wireless communication channels presentation.
Yeah, yeah. Afternoon session, we will show on,
Afternoon session is mine, no?
Yeah.
So, tomorrow,
yeah,
in his session you can ask.
yeah, yeah. Actually,
Because yesterday I have asked,
no, this is actually a part of 5G communication. So edge caching comes a part of 5G. So that's why we choose this topic. Yeah, yeah, yeah.
you have asked him yesterday, I mean, I informed them that you are more oriented towards research instead of teaching thing.
Yeah.
Yeah, that's why they are preferring this. Or you want to go for teaching side only? Algorithm? Yeah, professor have already discussed about this. Water filling algorithm yesterday or day before yesterday? So should I explain about it or should I continue with the next things? Yeah, because now, I mean, how many of you don't know about water filling algorithm? Yeah, I will tell you in which way you can write the research papers for this simple thing. Is that okay for you? Okay then. Water filling algorithm means, let us say, yeah, the cell phone is there. The cell phone is having a battery power of 0.5 watts. So, but at the same time, the cell phone has to send the signal. So, how much power that cell phone can use to the maximum extent for that video transmission or for talking to the base station? Yeah, whatever battery power is there, only that battery power only it can utilize cell phone. Or if you say, the cell phone is there, the cell phone is sending a video over the Bluetooth, this cell phone is sending a video over the Bluetooth to the other cell phone, let us say on ISM band. So, again Wi-Fi access point is sending its signal to the laptop. Remember, Wi-Fi also uses ISM band as well as Bluetooth also use the same ISM band. So, from the cell phone, if it is sending a Bluetooth signal to the cell phone will be creating interference to the laptop that is getting Wi-Fi signal. So, we have to control this interference also. Or we have to send the signal from the cell phone to the base station with the existing power only, with the existing battery power only. That's what is water filling problem. Here I am telling you again. So, how much capacity we can bear? How much capacity we can pass the signals? With how much data rate we can send the signals over any channel? That's what I am talking now.